Okay, so for this last video, we're going to consider kind of beefing up our code modeling section to also give you some choices in how you analyze your code. So as a reminder, the rest of this video is in this step 1 function. What we did in the last video was focusing on step 2 and expanding it to different types of asymptotic analysis. Now, before, when we were talking about code modeling, we did handwave a lot, and we'll continue to still handwave a little bit, because part of the thing that comes out of code modeling are these constant factors that we just don't care about in the end with asymptotic analysis. But what we showed you with code modeling doesn't allow you to model some really common pieces of code that we would use in maybe a data structures course like ours. So we're going to dive into this step 1 a bit more. Okay, so let's dive into before we talk about this idea that we're going to introduce called case analysis, let's consider a case study, what I'm going to call linear search. So linear search is an algorithm for taking an array and trying to find an element in that array. So I wrote a little Java program here to do this. Linear search takes an array and an int to find as parameters and loops them through the array from the start till the end. Once it finds the value you're looking for, it returns the index, and then returns -1 if it's not there. So nothing too complicated, but a very common type of program we would think about. And thinking about how to model this runtime, well, the runtime kind of depends on where the value that we're looking for is in the array. So, like for example, if I had this array 2, 3, 9, 4, 5, and I wanted to find number 2, well, we'd just return the index 0 right away. But if I was looking for the value 8, well, I would have to search through the whole array before returning at -1 that it's not there. So our first step in trying to do an algorithmic analysis on this is trying to come up with a code model, trying to identify what we think a function that describes the runtime in terms of the input size. So we have this code, we want to convert it to this function. Again, these runtime functions that we come up with take the input size n and return the number of steps or the number of operations that we need to do. And then we use that function for asymptotic analysis, right? But again, we're in this first part, just trying to come up with a function to describe this thing. So what would this function be? Well, we could use our steps as before, start counting up the simple steps. And remember, the exact constants I just put up on the screen don't matter, right? The difference between +2 is no different than a +3. We're actually going to start phasing these constants out soon as we start talking about these. So when you kind of see like just these specific numbers popping up for our code modeling step, don't worry if you don't understand why it's a +2 versus a +3, because all these numbers are made up anyways. It's just a constant number of steps. So we find the number of simple steps, but then there's a loop. So we need to figure out, how many times does this loop run? And we have the same problem as before with is prime, where we just don't know how many times this loop runs because it kind of depends. In one sense, this loop could run something like n times, right? This would happen if the value we're looking for is not present in the array. We'd have to search through the whole thing, and each iteration is something like 3 steps, and then maybe we have like 1 step at the end for the return. So we'd say something like this thing being order n, or big O of n. But in another, excuse me, in another real sense, it could also only run once in that case where we found the element right away at the beginning. And so these are 2 different functions to describe the runtime of the code here, right? One says it's going to run in linear time, and one says it's going to run in constant time. And so when would this happen? Well, the first one would happen if it's not present, and the second one would happen if it's at the beginning. The fact that we have to qualify these as happening in different cases motivates our need for introducing a context to our code modeling. So what we're going to be doing is introducing this idea of case analysis, thinking about different cases of your code, like if toFind is not present versus if toFind is at the beginning, and think about these as like 2 separate planet Earths, 2 separate universes. One of them, we always find the element at the beginning, and the worst case one is where we always find it at the end. So these 2 cases are totally valid. They could happen, but we're going to consider them separately. We're going to consider doing an analysis on them separately. So if you're in the best case on lucky Earth, your runtime function, no matter how big n is, you're always going to find it in one step, or I think here we have it in 2 steps. In the worst case world, on the unlucky Earth, where every year is 2020, no matter how big the array is, you're going to have to search through the whole array to find something that's not there. These 2 cases are completely separate and have completely separate runtime functions. One of them is f of n is equal to 2, and one of them is f of n is equal to 3n plus 1. Right? Just again, constants aren't going to end up mattering here, but that's what we had in our last slide. So this best case, worst case are just 2 completely separate models you're coming up with for your code. And remember, in code modeling, you take the code, turn it into a function. And then we always do asymptotic analysis afterwards. So we take that function and turn it into a bound. So you can do asymptotic analysis on each of these because these are separate code models. So for the best case world, you can find that our asymptotic analysis would say that this is big O of 1, big omega of 1, therefore it's also big theta of 1, because everything is just constant. And in the worst case world, you can also do asymptotic analysis on this one function, and you'd find that it's big O of n, big omega of n, and since those agree, it's therefore big theta of n. So now I want to talk a little bit more about thinking about this case analysis here. Thinking about these worlds is completely separate. So we're going to consider case analysis as identifying cases. A case is some description of the inputs or the state for an algorithm that's specific enough and important enough for you to build a code model around it. Remember, code models give us runtime functions. And remember, all those runtime functions we always come up with is a function that takes the input size as a parameter and returns the number of steps or the number of operations. So a case is a set, the state your algorithm could be in or the input your algorithm could receive, such that you want to produce your own code model for that one case where you come up with a completely separate function. Now, one thing important to mention is that case analysis is our tool for reasoning about all variations other than the input size n. Why is that? Well, the code model is a function that tells you the number of operations for any input size n. When you come up with a code model, that function describes what's the runtime for any input size n. For input size 0, for input size 10 million to 20 billion, that function describes the whole range of possibilities. These cases let you come up with different runtime functions, different functions that say what's the runtime for any input size n. And so you can't fix the input size for a case that needs to produce a function that allows any input size. We'll see this might be a little bit clearer in an example. So this importantly occurs at the first step, the code modeling step, when you take the code and turn it into a function. This does not occur in our asymptotic analysis step. You can still do asymptotic analysis afterwards, but asymptotic analysis has nothing to do with cases necessarily. It's just a follow-on. So we could come up with best case or worst case that our algorithm would follow based on its input size n. And importantly, you could come up with other cases too. Any position of the toFind value in the array could be its own case. So you can imagine one function for the best case world, which is that constant, another function for that worst case, and a bunch of other functions for every case in between. All of those functions would be upper bounded by big O of n because they're going to be better than the worst case by kind of our definition of worst being the worst. So they'll definitely be upper bound by O of n. But if you wanted to go analyze them, you'd have to go through each one and do a big O analysis, come up with the code modeling, and then do a big O or big omega or big theta analysis on that. We aren't going to really care about intermediate cases right now. They will become important later. But one of the things we're going to be identifying a little bit in this lecture and more in the following lectures is kind of identifying the most important cases, like the ones that you really should spend time analyzing and practicing how to identify what that case should be. And so usually we'll talk about best versus worst case. Now, before we explain this idea a little bit more about analyzing the parameters and coming up with cases, I want us to check our understanding of it and test ourselves. So consider that is prime example we did in the last video. Would we consider the prime versus not prime input for our runtime as separate cases in our is prime analysis? Just take a second and think about that and make a guess. Should we consider that or should we not? Take 1 second to think about that. Okay, so now that you're back, you could have said yes, you could have said no. It's pretty complex. So let me give you a bit of a reason why I would say we would not consider these separate cases. The reason is, when you do a case analysis, you're coming up with a new code model, a new runtime function. That runtime function tells you how many operations happen for any input size n. Now for the is prime example, there's only one runtime function, right? There's only one thing to change in that function, which is the size, the number we passed in. And so that is prime example only has one case. You come up with a function that tells you for any n, what's the runtime. Now that function is complicated, it like bounced up and down all the time, but it's just a single function. It's just one function. It gives you to give it an n, it tells you the runtime. In the linear search example, we had two completely different functions, right? For the best case when it's at the beginning, that didn't fix the size of the array. That function would tell you, no matter how big the array is, even if it's 1,000,000 long, it would still only take you 2 steps because it's right at the beginning. So that is a function that tells you, for any n, this is the runtime. Same thing for the worst case. When you have a really large array and the value is not there, you're going to have to search the whole thing. So that gives you a different runtime function that says for any n, what are the steps? The difference between these two examples is that linear search had other inputs on top of just the input size. So this gets back to something I said a little bit earlier, where we have been kind of brushing over the fact of what input size means. So for these simple int examples, we refer to the input size as being just the number that you passed in, and the runtime is going to be based on that number. Whenever we're talking about data structures, we refer to the input size as like the number of elements in that array or in that any type of structure. And so is prime only has one variation essentially. That is, what is the input size? While linear search, you can vary the input size and vary what element you're looking for and what's the data in the array. These variations lead to different runtime functions. And remember, the runtime function says for any input size, what is the number of operations? So that is the key difference here, is that in case analysis, we come up with different cases that lead to completely different runtime functions. For linear search, we have multiple functions over n because the runtime is affected by things other than that input n. And so for each function, we can do an asymptotic analysis. But for is prime, we don't do case analysis because there's only the input is the size itself. There's nothing else to vary. There's not two separate functions here. What we came up with were two different bounds for one really complicated function. Just like for a case analysis, you can come up with multiple bounds, upper and lower, for each of those functions. So that difference between a bound and a function is very, very important. And we'll come back to this over and over again. And it's okay if this is a bit confusing right now, because it's a bit weird when you think about it. Like the fact that there's different, we call those different cases for linear search, but not is prime, even though that is prime example, definitely looks a lot more complex. It's because the only thing we vary to make a new case is something other than the input size. So what we've just done now is we've now added another choice for you to do in your algorithmic analysis. Now your step 1 has some choices here where you identify which case you want to analyze. And you can analyze all of them if you want to, or identify a few and analyze those. But now for each case, you'll come up with a different runtime function, a function f that takes an input n and outputs the number of steps. And then for each of those functions, you can come up with a big O, big omega, big theta bound. And so now you have choice. One reason we want to separate these is sometimes when we introduce this terminology of like best case versus worst case, sometimes people can mix those up with big O and big omega, but those are completely separate concepts. Big O, big omega come in the asymptotic analysis step. where you're taking a function and finding an upper or lower bound. While case analysis happens in the code modeling step, when you take a piece of code and you come up with a function, and you can identify different cases that would result in different functions. Okay? So we're going to get more practice with this in lecture because this was a bit confusing, and we promise we'll revisit this over and over again because this is a very important distinction.